Welcome to homework.
This is the answer to chapter 22, problem number 65 from the Smith Organic Chemistry textbook. And this problem this problem tells us that acid-catalyzed hydrolysis of this molecule forms compound A, which shows a strong peak in its IR at 1770 wave number. And then we're given some NMR spectra as well. And we're asked to draw the structure for A and draw a stepwise mechanism that accounts for its formation. Okay, so I'm actually going to move the NMR piece over. All right. So first of all, we're given a formula C6H10O2. So the first thing we can do is calculate the HDI. Or the unsaturation number, or the degrees of unsaturation. And so that's going to be 2 times the number of carbons plus 2 minus the number of hydrogens. So we get 14 minus 10 is 4. All of that over 2. So our HDI equals 2. So we have 2 rings, 2 double bonds, or a ring and a double bond. Okay. So next, looking at the IR, the only thing we get from the IR is a peak at 1770. And so this suggests a carbon-oxygen double bond. Okay. And certainly that could explain one of our degrees of unsaturation in this molecule. Okay. So now looking at the NMR, we have a 1.27 ppm singlet with an integration of 6. This to me suggests 2 methyl groups, and obviously they'd be equivalent since they're giving just the one signal there. So then we have a 2.12 ppm triplet with an integration of 2, and a 4.26 ppm triplet also with an integration of 2. So these are both triplets, and they both integrate to 2. And so I think that these are 2 methylene groups, and I believe that they are splitting one another. So 2 methylene groups splitting one another would look like this. We have a carbonyl somewhere in this molecule. We also have a second oxygen to account for. So I think that we have an ester here. And so one way that we can put this all together to get our 6 carbons, 10 hydrogens, and 2 oxygens accounted for, and in a way that's going to make sense with our NMR, would be if we have a lactone. And so it's going to be a lactone with 2 methyl groups here. And so obviously the signal for our methyl groups are going to be the methyl groups. And then our first triplet with an integration of 2 is going to be the 2 protons on this carbon. And then our one that is further downfield is going to be the methylene group that is attached to an oxygen. And that's why it's so de-shielded. Okay, so there's molecule A. And now, as far as a mechanism that accounts for its formation, that's going to look like this. So the first thing that's going to happen is going to be that a molecule of water is going to add to this carbon of the nitrile. And so after that first step, we will be right here. And so the oxygen is only going to have one lone pair, and it's going to have a positive charge. And our nitrogen is now going to have 2 lone pairs, and so it is going to have a negative charge. And to resolve those charges and make everything have the number of bonds that it wants, we can just call this formally a proton transfer. Okay, and so the result of that is going to be this molecule. Okay, and the next thing that's going to happen here is that this nitrogen is going to get protonated. And so to do that, we'll use some of the acid that we have in this molecule, or some of the acid that we have in this reaction, rather. Sorry. So this nitrogen will get protonated like this. And the result of that will be this molecule. And so now the nitrogen is going to have no lone pairs, and it's going to have a positive charge. And actually, let me change the way that I drew this. So what can happen next is simultaneously this hydrogen on the alcohol can be grabbed by a water molecule. And at the same time, one of the carbon nitrogen bonds can break. And so the result of this is going to be the formation of an amide. Okay, so we have an amide now. The next thing that's going to happen is going to be protonation of the oxygen of our amide. And so again, we do have acid in this reaction. And so the acid can carry that out. Okay, and so the oxygen now has one lone pair and a positive charge on it. And of course, when a carbonyl oxygen is protonated like that, it makes the carbonyl carbon more reactive. And so that is going to allow this alcohol on the other side of the molecule to come and attack that carbon. These electrons from the carbon oxygen double bond will revert to the oxygen. And so now we have formed our ring, which is good, right? Because we said the product molecule A was a ring. So it's good that we've started to form this ring. Okay. So we have our tetrahedral intermediate here. This oxygen has one lone pair and a positive charge. Okay. And so the next thing that's going to happen is deprotonation of that oxygen. And so again, water can pick up a proton there. Okay. All right. And so from here, we're going to protonate the amine, which is going to make it into a good leaving group. I guess I should have written a little smaller because it looks like I am about to run out of space. So I'm probably going to have to finish this problem on a third page. But so anyway, our nitrogen has been protonated. Well, maybe I can. Nah, I can't squeeze it all in. All right. So our nitrogen has been protonated. So what's going to happen now is the lone pair from this oxygen is going to add in to reform the carbonyl, and simultaneously the nitrogen will leave with those electrons from that carbon-nitrogen bond. And so continued on the third page here, that will get us to this intermediate. And the very last thing that needs to happen is deprotonation here. And that can be accomplished by water yet again. So you see the utility of water in these systems. It can accept a proton, and after it's accepted a proton and it's the H3O plus, it can donate a proton. So it serves almost as a buffer in some of these organic reagents. Some of these organic reactions, rather. Okay, and so this is now our final product, A. So again, here on page 3 is the final step, which is just a deprotonation. Here on page 2 is the rest of the stepwise mechanism. Okay, and then here on page 1 is the formula and spectral information that we used to deduce the structure of A, which happily agrees with what we got when we worked it out mechanistically. And that's the answer to chapter 22, problem number 65.